So the very last thing that we did in the last lecture was learn how to draw Lewis dot structures using those 6 steps. Draw the skeletal structure, count your valence electrons, subtract by the bonds you drew in your skeletal structure, add any remaining electrons to complete the octets of the terminal outside atoms. Then if there's any left over, put it on the central atom. And finally, if your central atom does not have an octet, move lone pairs to make a double bond there. So I think the last thing we did was carbonate, but it's very similar setup to the nitrate ion, which was the example out of the textbook. Nitrate. Yeah, let's do carbonate. This was the very last thing that we drew was the carbonate ion using those 6 steps. We had a carbon, 3 oxygens, and we found that we had a lone pair to one of them, doesn't really matter, or sorry, double bond to one of them. And then overall, the carbonate ion has a 2- charge. So last time we showed that charge by putting it in brackets and a 2 on the outside, which isn't technically incorrect, but if you're entering these into Connect, for those of you who already started working on the homework, it does not let you put brackets around entire structures. So how do you show the charges when it's an entire molecule that has the charge rather than a single ion that has the charge? And that's leading into section 8.6 with formal charge. So I'm on page 345. So the concept of formal charge is the idea of yes, these are covalent bonds, they're molecular structures, but if they were ionic, what would be the charge if I were to reach into that structure and pull that particular atom out of the structure? Just rip it out, what would its charge be? And we learned back in chapter 2, the charge is going to be the difference in how many electrons it was supposed to have versus how many it actually has. If it has more electrons than it originally had, you end up with a negative charge. If it has fewer electrons than you originally had, you ended up with a positive charge. Same rules are going to apply here. So formal charge, I'm just going to put FC for short, is equal to the number of valence electrons, since they're the only ones involved in bonding anyways, and that's just going to be the group number. So group number 1, 1 valence electron, 2, 2, group 6, 6, etc. Subtracted the number of associated electrons. And the associated electrons are the ones that if I were to reach into that atom and pull that, or reach into that molecule, pull that atom out, how many would it get to keep? So if I'm looking at a structure, it would get to keep any of the lone pair electrons. And if you picture, say, I were to come in here, change colors real quick, and say I were to rip this oxygen out of there, it would get to keep its lone electrons, and then these, how many electrons is it sharing with the carbon? How many electrons are being shared there with the carbon? 4, good. Each bond is 2 electrons. It's got double bonds, so it's got 4 electrons being shared. When I rip that oxygen out of there, it's like a 50-50 divorce. It gets to keep half of any shared assets and any of its own assets. So these lone pairs of electrons are its own assets. These 4 shared pairs are the shared assets, so it gets to keep half of them. So associated electrons are going to be all lone pairs. Plus half of the bonding electrons. So a quick way is count 1 electron per bond. Now, most of the time, you're going to find most things, at least stable configurations, are going to have formal charges of 0. If we look at this oxygen right here, how many valence electrons does an oxygen start with? 6, good. It's in group 6, so it started with 6 valence electrons. So 6 valence electrons minus how many are associated with this particular oxygen? Also 6, good. It's got 2 4 lone pairs, and then if I count 1 per bond, then I'm up to 5, 6. So it has a formal charge of 0. So that oxygen has a formal charge of 0. What about carbon? How many valence electrons does carbon start with? 4, it's in group 4. How many are associated with this carbon? If I were to pull him out, how many electrons would he get to keep? 4, good. Count 1 per bond is the quick and easy way. And he doesn't have any lone pairs, so he just gets 4. So he also has a formal charge of 0. In most stable structures, carbon's going to have a formal charge of 0. That's the best structure for carbon, is with a formal charge of 0. Now let's look at this oxygen over here on the end, this one here. It has, again, its oxygen starts with 6 valence electrons, but how many are associated with this one? 7, good. 1, 2, 3, 4, 5, 6, 7. 7, so it has a formal charge of -1 there. This oxygen on the top, what would its formal charge be? Also -1. It's going to end up being the same thing. 6 minus 7 is -1. So if I were to, say, redraw, let's make it a little bit prettier. Carbon, oxygen, oxygen, oxygen. And then assign the formal charges. This oxygen off to the side would have a -1 formal charge, and this oxygen up here would have a -1 formal charge. And that's how you would put it in to connect on ChemDraw, is you would assign the formal charges to the individual atoms. What that means is when you're assigning those charges, just like if you were doing a lone pair, I hope everybody watched my videos, otherwise you have no idea what you're doing with ChemDraw right now. You have to highlight over the atom until you see that blue highlight, and then it knows you're attaching that lone pair or that bond or that formal charge to that specific atom. If your atom has 2 letters, such as chlorine is Cl, highlight over the first letter, the C, because ChemDraw at this time won't let you highlight both letters. So this is the formal charge. Now, rules about formal charges. The sum of the formal charge must add up to the charge on the overall molecule. Carbonate, overall charge of 2 minus. Did my formal charges add up to that? Yes, it did. So that's how to assign formal charges. Any questions about assigning formal charges? So why are formal charges so important? Formal charges are so important because they tell us what structure is the most stable or the best structure. So let's look at some rules here. So these rules, by the way, are on the bottom page 346. So when I'm looking at a structure and I've followed my 6 rules to draw out its Lewis structure, sometimes I find that I can satisfy all 6 rules in more than one way. Maybe that's changing it from having 1 center to 2 centers. Maybe that's changing around where a double bond is or where a lone pair ends up. As long as everything ends up with an octet, it's fine, right? But how do we know which structure is the most likely structure? We assign formal charges and then follow these 3 rules. So the first rule is for molecules, why they say molecules, they mean compared to for molecules, so not polyatomic ions like we just saw, Lewis structures in which all formal charges are 0 is preferred to things that have non-zero formal charges. Now again, because formal charges have to add up to the charge in the molecule, if you have a polyatomic ion that has a charge, this rule is impossible. So that's why it's got the disclaimer for molecules. But if you can pull off a structure, not always possible, where everything has a formal charge of 0, that is always going to be the preferred structure. The second rule, kind of building up from that, is, well, if it's impossible to get everything 0, at least get them to be small charges. So 0s and plus or minuses 1s. Bigger charges, +2, +3, etc., those start making it unstable because that means the electrons are not very evenly distributed and they're going to lean more one way than the other and get closer to being ionic. The last rule is all other things being equal, the best skeletal structure is one in which the formal charges are consistent with electronegativities. So people go, what on earth does that mean? Consistent with electronegativities. We learned last time that electronegativity is how strongly an atom pulls electrons towards it. If you're looking at the periodic table, electronegativity increases across the row and decreases down the family. So the most electronegative element we have is fluorine. We had that little table, had electronegativity values. Fluorine was 4.0, hydrogen was 2.1, etc. So the more electronegative an element is, the more strongly it pulls electrons towards itself, so the more likely it will have a negative charge. So that means the more consistent with electronegativities means the more negative formal charges go to the more electronegative element. Negative formal charges go to the more electronegative element. So let's try an example where we're trying to figure out what the best structure would be using these rules. And I'm going to do, let's do on page 348, checkpoint 2. So this question asks which of the following Lewis structures shown is the most likely preferred for the polyatomic ion NCO-. So here are the 5 possible structures. Now for all of these, carbon's going to be in the middle since carbon has the most possible bonds. Usually carbon's in the middle anyways. So the first one is it double bonds out to both of those elements on the side. The second possibility is that it's going to single bond to the nitrogen, but then triple bond to the oxygen. Third option is going to switch that. Triple bond to the nitrogen, and then a single bond to the oxygen. SU. D and E aren't that great of structures automatically. We'll look at them real quick and show you why we can probably go ahead and discount these. So right off the bat, what is so wrong with D and E that we can probably go ahead and say those are not good structures? Look at the carbon. Has 3 bonds, so what does that mean about its octet? Does carbon have a complete octet? No, and all both of those structures, this carbon in the center has only 6 electrons. It does not have an incomplete octet. Does not have a complete octet. So we can already go ahead and discount that those are not good structures. Carbon likes its octet. It also likes to have 4 bonds. So we can go ahead and cross out. So now there are 3 options. A, B, and C. Right off the bat, which one looks the most stable to you? Why? If you knew nothing about formal charge, you'd probably want to pick A, right? Why do people like to pick A? Looks even, right? Looks like you even it out. But the thing is, it's not even because are nitrogen and oxygen equivalent? No, they're not equivalent. They're not the same element, so it's not technically even. Though it looks even because it's double bonds on both sides, it's not technically even. So we're going to assign formal charges to determine actually which one is the best structure here. So again, formal charge is the number of valence electrons minus the number of associated electrons. So let's look for this first structure. Nitrogen. How many valence electrons does nitrogen start with? Where is nitrogen on the periodic table? Group 5, so it starts with 5 valence electrons. So nitrogen's formal charge is 5 minus how many are currently associated with this nitrogen right here? 6. So it has a formal charge of what? -1. So that's got a formal charge of -1. Carbon in the middle. Like most structures that are stable, this carbon is going to have a formal charge of 0. 4 minus 4. Oxygen on the side there, oxygen starts with 6 valence electrons. How many are currently associated with this oxygen? 6, so it ends up with a formal charge of 0. So at first blush, all the formal charge rules apply. I've got only one formal charge of -1 on that nitrogen. That adds up to the charge of -1 on the overall structure. Everything still looks okay. Now let's look at the second possibility down here. Nitrogen, again starting with 5, but now how many are associated with this nitrogen? 7. So it has a formal charge of -2. Carbon still 0. This oxygen, what would its formal charge be? -1 or +1? So 6 valence electrons. How many are currently associated with this? 7. Oh, that's because whoops. Let's see. Where's my eraser? Man. I'm looking down at my notes, not paying attention to what I've got written up here. All right, so pretend it looked like that the whole time. Now, what's this formal charge? +1, good. So 6 minus 5 is equal to +1. So did the formal charges still add up to the charge on the overall molecule? I've got -2 and +1. Yep, they still add up. But why is that probably right off the bat not going to be a great structure? It's unstable. Why? Good. -2 on the nitrogen is back to this rule over here. Come on, click that. I clicked on it. Low structures with small formal charges are preferred to those with large formal charges. So that -2 is considered a large formal charge. All right, let's try this very last one here. This nitrogen has how many associated electrons? 5. So what's its formal charge? 0. Well, oxygen has how many associated electrons? 7. So it has a formal charge of what? -1. So of those 3, A, B, and C, B is definitely the worst structure, but between A and C, which one is the better structure? And why? Why? Which one's more electronegative, nitrogen or oxygen? Oxygen is more electronegative, so there's a key here. O is more electronegative than nitrogen. Which means which one should get the negative formal charge, oxygen or nitrogen? Oxygen. So which is the best structure out of these? C. So the correct answer here is C is the best structure because it's consistent with electronegativities. The oxygen's more electronegative and it got the negative charge. So if I asked you a question that asked which of these structures is the most likely arrangement, assign formal charges and then assign those 3 rules. Questions about that? Let's look back at this structure here. Actually, let me grab all this stuff and pull it away. Move away. There. All right, so back to our carbonate ion. What if I had drawn it like this? Now the formal charge of -1 and -1 are in those two oxygens. Could I use formal charge to determine which one of these is the best structure? Or would they both be equivalent as far as formal charges go? They're equivalent as far as formal charges go, so both structures are equally likely. I could also have drawn it this way, with the double bond pointing to the upward oxygen. All three of these structures, although they are different, are equivalent as far as formal charges go. I know that because I'm moving a double bond, which was the same thing I did in the last example, except that I'm moving it between the same element. All three of these are oxygens. When you have this happen, where it's, according to formal charges, basically equivalent structures, we call this resonance. And we show that these structures are equivalent with a double-sided arrow. Not the same thing as the double-sided arrows we saw in acid bases when we said that the reaction was reversible, but a single arrow that just has two ends, like that. That is a resonance arrow. The arrow that says the reactions are reversible was like that, two arrows pointing in different directions. Resonance arrow is one arrow that has two ends. So we're getting into section 8.7, resonance, on page, still on the page 348. So all that I need you to know is be able to recognize when structures are resonance structures. I'm not going to ask you anything too in depth about resonance. If you go into organic chemistry, you will spend lots and lots of time on resonance. Just be able to tell me that they are resonance structures. And this almost always, and at least in our class, is going to occur when you've got a double bond that can be moved between different atoms in a structure that are the same element, such as in this case, oxygen. We just moved that double bond from one oxygen to another. And that's the general idea of resonance. So now that we've talked all about Lewis-Dot structures, let's talk about all the times we're going to break all those rules. Exceptions to the octet rule, section 8.8 on page 350. So the octet rule, just to reiterate, is the fact that all of the elements are going to want to have 8 valence electrons, except for hydrogen just wants 2, because they want to look like the nearest noble gas. When we were going over the 6 rules of drawing out Lewis-Dot structures, there was this one little disclaimer we had on the rule 6 when we said that we need to have the central atom have an octet. We could do that by rearranging to make double bonds, unless the central atom was group 3. So the classic example of a group 3 element that does covalent bonding is boron. The same thing could happen in group 2. Beryllium is technically a metal, so most times it's going to make ionic bonds unless it's with a element that is very low in electronegativity, such as hydrogen. It can technically make covalent bonds like we see here. So this boron right here, this boron only has 6 electrons available to it. But we learned when we were first doing Lewis-Dot structures, if I draw the Lewis dot structure for boron, boron can only make 3 bonds. So that's why this occurs. This is something called an incomplete octet. An incomplete octet is when you end up with an element or an atom in the structure that just doesn't have an octet. This pretty much always happens in group 3, or in the case of beryllium, it can happen in group 2. So beryllium and boron, the main examples of incomplete octets. There's also a special case of incomplete octet called an odd number of electrons. So far, when we were doing all the rules of drawing out Lewis dot structures, we always move electrons in pairs, whether it's lone pairs, that's 2 electrons, or a bond that requires 2 electrons. Well, what if when you added up all your valence electrons, you ended up with an odd number? Like, for example, let's look at the NO2 molecule. Change color. We'll do this color. NO2. If I added up the number of valence electrons for the NO2 molecule, nitrogen has 5, oxygen has 6 times 2, because there's 2 of them. How many valence electrons are in this molecule? 17. That's an odd number. 17 electrons. Now, this might have ended up being, say, an ion, a polyatomic ion like nitrite, which would have a negative charge, and that would fix the problem. But in this case, we're not looking at it as an ion. There's no charge on that thing. We have 17 electrons. There is no way for us to make this structure without being left with an extra electron. This extra electron we're going to put on the central atom right there. So with all of our exceptions to the octet rule, if anything breaks the octet rule, it is always the central atom. So disclaimer, only the central atom can break the octet rule. That's why when we did our 6 rules of drawing out Lewis dot structures, we took care of the octets of those terminal atoms first. The central atom is on the inside of the structure. It's kind of shielded from the outside world, which allows it to be more likely to be, if it's unstable, it's still okay for the overall molecule. The part of the molecule that's reaching towards the outside is still stable. So if you have an odd number of electrons, stick that odd number on the central atom. Now, this is still an incomplete octet because in this structure, this nitrogen only has 7 electrons. So it's a kind of incomplete octet. Now, these things are incredibly unstable. These things are referred to as free radicals because they're so unstable they will bond with anything they get close to because they want to get rid of that lone electron, or they want that lone electron to bond with something. They're just running around like a piece of sticky paper that will stick to anything. Now, where have you heard the term free radicals thrown around all the time? Popular culture and commercials. Where do we always hear it associated with? Free radicals, they're going to kill us. What are they? What do commercials make them look like? You guys don't watch commercials anymore? Oh, come on, even YouTube has commercials. What kind of commercials are always throwing around the term free radicals? Things like antioxidants, things like, eat this goji berry juice. It is going to, have antioxidants that are going to bind with the free radicals and stop your body from breaking down. Or the other one, you see a lot of it, is anti-aging creams. Free radicals from the sun are aging your skin. Use our lotion and you'll reverse the process. So free radicals come from a lot of different sources, but one of the large sources of them is solar radiation. And so that is why being out in the sun a long time without protection does prematurely age you, because those free radicals will start bonding with your chemistry in your body, with your molecules in your cells, and start disrupting the cellular processes, which cause the cells to start breaking down and then dying, and then things start not working like they're supposed to. So these free radicals will bond with anything, although if they come across another free radical that looks just like them, that is the best possible scenario because they'll just bond with themselves. So back to our connect the dot Lewis dot structures, connect these 2 dots. And we now have a larger molecule, dihydrogen tetroxide here. So those are the both incomplete octets. There are a very limited number of incomplete octets examples you can have. Most of the examples we're going to deal with this class is the third kind of exception, the octet rule, which is an expanded octet. So let's jump ahead to an expanded octet. So if an incomplete octet, the central atom has fewer than 8 electrons, what do you think an expanded octet is? Has more than 8 electrons, right? Let's play opposite day. More than 8 electrons is the opposite. So how on earth can this happen? We said way back we were doing chapter 6 and then leading into chapter 7, the reason we can only have 8 possible valence electrons, or a maximum of 8, is because our valence shell is always the s and the p. And s's have a maximum of 2 electrons, p's have a maximum of 6 electrons, and that adds up to a maximum of 8 valence electrons, because you don't start filling those D's until you go on to the next shell and go back to S and reset yourself. But once you get to the third period, we have 3S, 3P. We also have 3D. Now we learned in chapter 6 that D doesn't get filled until we go down to the fourth period and we start filling the D shell anyways, but that doesn't mean it's not still there. 3D is there, it's just sitting empty. It's just sitting there empty. It's technically there though. So if your central atom is third period or below, it does have a D subshell. It just is sitting there empty, but you can technically bond into it. So in our example here, we have sulfur in the center. Sulfur is third period, so it does have a 3D subshell. Sitting there empty, you can technically bond into that subshell. And we're going to see in chapter 9 in greater detail exactly what this looks like when they bond into that D subshell. So in this structure, we have SF6 here. So we ended up with how many electrons around this sulfur? How many electrons does that sulfur have access to? Each line is how many electrons? 2. How many lines are there? 6. What's 2 times 6? 12. I know. The math is coming. Here it is. 12 electrons. So 12 electrons right here, so that is an expanded octet because 12 is greater than 8. So to determine for this section, what I want you to do is be able to draw the Lewis structure following our rules from the last section, 6 rules, and then tell me whether or not it obeys the octet rule. So in this case, no, it would not obey the octet rule and is an expanded octet. Let's try some of these. Draw the Lewis structures of the following. Now I'm going to do, just looking at the skeletal structure, we know boron is going to be an incomplete octet because it can't have more than 3 bonds anyways. Just looking at this second structure, before you even finish the octet, you can already, or finish the 6 rules, you can already tell it's going to be an expanded octet because just from the skeletal structure, it's going to end up with how many electrons from the skeletal structure around arsenic? 10. Now let's look at the last one. If I stop at the skeletal structure, it looks like xenon's got a perfect octet. It looks like it's got 4 bonds, 2 each. It looks like it has 8. So here's a mistake I see students making. They stop there and say, oh, it's got 8 electrons, it obeyed the octet rule. The skeletal structure is only the first step in drawing the Lewis dot structure. So don't skip the other steps. So let's go ahead and complete the structure here for Z, xenon tetrafluoride here for C. So the second step then is to count up the electrons. How many do we get from xenon? 8. Yes, it is a noble gas. Some of those noble gases, especially lower on the table, technically do bond. How many do we get from fluorine? 7 times. We have 4 of them, so 28. So how many electrons do we have to play with? 36. Good. How many have we already used making this skeletal structure? Reach these bonds is 2 electrons. How many have we already spent? 8. So subtract off 8 for the bonds. Now we're down to what? 28 again. what's the next step? What do I start doing with those extra electrons? Where do I put them? On the fluorines. Good. Terminal atoms. So each of these fluorines only has 2 electrons. It wants 8, so I'm going to give each one of them 6 more. So how many electrons am I going to spend to give each fluorine an octet? 24. Good. So I still have 4 electrons left. What am I going to do with those 4 electrons? Put them on xenon. So step 5 was if you have any remaining electrons, put them on the central atom in pairs. So you wouldn't just put 1, 2, 3, 4. You would put 2 pairs of electrons on xenon, there and there. So now, how many electrons does xenon have access to? Xenon has how many? 12. It has 12 electrons. Does this obey the octet rule? You're not sure. Obeying the octet rule would mean it has how many electrons? 8. Is 12 equal to 8? No. So do you feel confident about answering whether or not this obeys the octet rule now? Yes. Does it obey the octet rule? No, it does not. Good. So that's what I need you to do from this section. Draw the Lewis structure. Tell me if it obeys the octet rule. And by the way, when you're drawing these in Connect, I put this in the video, but if you might have missed it, when you have a central atom that has 2 letters, such as xenon has 2 letters here, ChemDraw will let you either add the bond to the X or the E. You need to add it to the first letter. One of your homework questions commonly gets counted wrong, and this is usually the culprit. The first letter is the one you have to bond to. And that happens when you go to add this bond. It's so easy to accidentally bond it to the E. Make sure you actually highlight the X and have it bonding to the first letter. I don't know why ChemDraw makes that distinction, but it does for some reason, and that can cause it to count the whole structure wrong. But of course, if it's counting it wrong and it looks completely right to you and it looks like the answer key and you still don't know, please don't spend 5 hours today beating your head against this. Just send me an email. If it looks right to me too, I'm fine with giving you the points. But if you email me asking me for help at 10 p.m., I might not get to it in time. Any questions about the exceptions to the octet rule? One more section in Chapter 8, and then we're done with Chapter 8. So the last section of Chapter 8, let me go back to my blank screens, is going to be bond enthalpy. There. So let's see what we remember from Chapter 5 about enthalpy. Enthalpy. What is let's start small. What letter do we give for enthalpy? What letter is it? Delta is change, but delta what? H. Good. Delta H. So delta H is the change in enthalpy for, say, a reaction. So a chemical reaction has a change in enthalpy. In Chapter 5, we had several different ways of calculating the enthalpy of a reaction. The last way is through those enthalpies of formation, the standard enthalpies of formation we got in the appendix. And we had this little equation to find the standard enthalpy for Rxn, a reaction. It is the sum of the standard enthalpies F of formation of your products minus the sum of your standard enthalpies of formation of your reactants. Where you found those standard enthalpies of formation in the appendix in the back. Look familiar? We've seen it. We can repeat that on the exam in a couple of weeks. Sure. Oh, don't remind me, no. The good news is we're so close to the end. Just got to get over that last hill. I think I can, I think I can, I think I can. So this is if you have the standard enthalpies of formation for the entire compound. Now we know that we actually have what's going on in these chemical reactions isn't just forming compounds, but we can now look at the sub-molecular level at the individual bonds. So if I have a chemical reaction, reactants go to products. Go to products. What's actually going on here is that I'm breaking the bonds of these reactants. Because I want to rearrange the atoms, right? Way back to chapter 2, Dalton, he was talking about chemical reactions rearrange the atoms. So before we can rearrange them, we have to break them apart. So we're going to break those bonds of those reactants. And then on the other side of the reactants, or on the other side of the reaction here on the products, what are we doing on this side? If we're breaking bonds on this side, what do you think we're doing on this side? Making bonds. Good. So on this side, we're going to form bonds. So breaking bonds, do you think that takes energy or releases energy? Breaking them. Taking energy or releasing energy? Does it release energy to break a bond, or do you think it takes energy to break something? It takes energy. It requires energy. So it requires energy to break a bond. Required energy. While the opposite, as we learned in chapter 5, if you do the opposite of something, it's also going to be the opposite sign of delta H. So over here, forming bonds is going to do what with energy? Require it or release it? Release it. Good. So if breaking bonds requires energy, what did we learn about requiring energy as far as the sign of delta H? Is it positive or negative? If it's requiring energy, is it positive delta H or negative delta H? So if I'm requiring it, I'm pulling it inward to me. Is that positive or negative? Positive. Good. Delta H is positive. So over here, forming bonds, delta H would be what? Negative. Good. We're doing the opposite, so we're going to switch the sign. Negative. These delta H values are called bond enthalpies. Bond enthalpies is the energy it takes to break or form a bond. It's going to be positive if you're breaking the bond, and negative if you are forming the bond. Those are your bond enthalpies here. We have a table of bond enthalpies on page 355. So we don't have to worry about going to the appendix. Page 355 has all of our table of bond enthalpies. Let me switch back to the slideshow so you can see what that looks like. So here's our, on page 355, top half and the bottom half of our table here. And there's our bond enthalpy. So these are all in kilojoules per mole. So to break the hydrogen-oxygen bond right here takes 460 kilojoules per mole, etc. Or to form it releases 460 kilojoules per mole. So I'm going to ask you to calculate the change in enthalpy for the reaction again. But now, our new equation here is going to look like this. Delta H is equal to the sum of, we're going to say BE for bond enthalpy, of our reactants minus the bond enthalpy of the products, which looks like the opposite of the equation we had in chapter 5. But the reason for that is, what we just worked out, reactants are breaking bonds, so their delta H is positive. Products are forming bonds, so their delta H is negative. So that's why we have a big minus in between here. The products are going to be minus because those are forming bonds, which is releasing energy. Now, this is per bond. Bond enthalpies are per bond. So you can't just look at the molecular formula in most cases and automatically know what the bonds are. We have to draw the Lewis dot structures. to see what kind of bonds are there. Are they single, double, triple? How many bonds are in the structure? Because the bond enthalpies, these values, when we go to put them in, these are all per bond. So a couple of notes about this table. Notice that some of these structures are shown in pink. Those that are shown in pink are different because that is specifically talking about the bond enthalpy in a diatomic molecule. So diatomic means the entire molecule is just 2 atoms. So for example, if I'm looking here at the carbon to oxygen single bond here, let's go back to the slideshow. Let's do that. So carbon to oxygen right there is shown in pink, which means it's a diatomic molecule because that's carbon monoxide. So that's not in a larger structure. That's just for the molecule. Whereas if I look down here to carbon to phosphorus, shown in black there, that could be part of a larger structure. So that could be one carbon phosphorus single bond in a larger structure. So that's why some of them are shown in pink. The other important thing to note about this table is down here in the very bottom left-hand side, look at the carbon-oxygen double bond here. It's got a little disclaimer mark here. So for those of you who have your books open at page 355, what is the disclaimer for carbon-oxygen double bond? What's that disclaimer mean? Is it important to read disclaimers? Yes, very important to read disclaimers. There's a reason I'm pointing this one out, because I use carbon-oxygen double bonds a lot in these, and if you use the wrong number, you get the whole problem wrong. So I'm pointing it out for a very important reason. So the disclaimer there on page 355 says that the carbon-oxygen double bond in CO2 is 799, not 745. So if you have carbon-oxygen double bond in a larger molecule, then yes, it is 745. But if it's in carbon dioxide, it's 799. That's because carbon dioxide is an incredibly stable molecule. It takes a little bit of extra energy to break it. So that disclaimer is very important because, hey, we're going to use carbon dioxide a lot, and if you're not paying attention and use the 745 for carbon dioxide, you'll get the whole problem wrong. And if this is a multiple choice test, I guarantee you the answer, had you used the 745, is going to be sitting there trying to tempt you. All right, ready to try this out? Let's try this out. Let's see. Let's find the enthalpy of the following reaction. Let's do the combustion of methane. CO2 and H2O. So there's our happy little combustion reaction. This is methane. Now, before we can do anything else, we need to make sure this is balanced. It's not. So I'm going to need 2 oxygens, and I'm going to need 2 waters. And now it's balanced. The question is, find the enthalpy of this reaction using bond enthalpies. So if I look at my table of bond enthalpies, and here's why I have a lot of students like raising their hand on the test like in a panic, and I'm like, you didn't practice this when you were studying, did you? And they're like, it says to use the bond enthalpies, but when I look at the table of bond enthalpies, I'm not seeing CH4 anywhere. I don't see CH4 anywhere because is CH4 a bond? No, it's a molecule. These are bonds. So before you can assign bond enthalpies, we have to see what the bonds are, how many are there, and whether or not they're single, double, or triple. Don't just look, oh, it's a carbon-oxygen bond. Well, there are several different kinds. There's actually 4 different kinds of carbon-oxygen bonds: single, double, triple, and carbon dioxide. So be very careful here. So let's draw this out. So carbon, most of these molecules are small enough we can go back to the connect the dots method of drawing out Lewis dot structures. So carbon here, 4 dots. So what kind of bond is it going to be to hydrogen? Single, double, triple, what? Single. So we'll just come in with our hydrogen dot, draw a line. Come in with our hydrogen dot, draw a line. Dot, draw a line. Dot, dot, draw a line. So the bond there is a carbon-hydrogen what? Double, triple, single, what? Single. So I have a carbon-hydrogen single bond. How many do I have in this reaction? 4, which means when I take the bond enthalpy of carbon-hydrogen single bond, I need to multiply it by 4 because I'm breaking 4 of these things. So I multiply by 4 there. O2. Bond between 2 oxygens, is it single, double, or triple in the O2 molecule? Double, good. Now, notice the coefficient there too that says I have 2 of these things. So I have 2 of the molecules. So because I'm a visual person and I will miscount if I don't do it, I'm going to draw 2 molecules. So I don't miscount. So I have an oxygen-oxygen double bond. If you really want to include all the lone pairs just to make it technically correct, each of these oxygens also have 2 lone pairs. And I've got 2 of them because I have 2 molecules and each one of them have 1 bond. Over here, carbon dioxide, that's carbon in the middle, double bonded to an oxygen, double bonded to an oxygen. So I have a carbon-oxygen double bond. How many of them do I have? How many? 1, 2, 3. How many carbon-oxygen double bonds do I have in the reaction? 1 or 2? Let's circle them. 1, 2. 2. Another common mistake I have. They go, well, there was 1 molecule, yes, but the molecule had 2 bonds. So we had to form both of them. All right, H2O. Oxygen in the middle, hydrogen, hydrogen. I might do that in black. I've got 2 of them, so just like with the oxygen on the other side, I'm going to draw it twice. So I have 2 of them. So I have an oxygen, hydrogen, or hydrogen, oxygen, single bond. How many of those do I have? 4, good. 4. 1, 2, 3, 4. That's why when I have a coefficient that says I have more than one of the molecule, I'm going to draw that molecule more than once. It helps keep me from miscounting any of these bonds. Now, over here are my reactants. So these bonds are being broken. And over here are my products. So these are being formed, which means the products are going to be negative. So I'm going to put brackets on these and say this whole thing is negative. I'll just put brackets over here for good measure. Now all I have to do is go back to the table, pull those numbers, and plug them in. So carbon to hydrogen, single bond. If I go to my table, carbon to hydrogen, single bond. Second half, there it is. 414 right there. Now oxygen to oxygen, double bond. Oxygen, oxygen, double bond, and it's in pink. What does it mean that's in pink? Diatomic molecule. So that's for the O2 molecule, which is good because that's what we've got. So 498.7. Minus, open brackets. Now, we have carbon-oxygen double bond. So going to our table, Are we going to use the 745 or are we going to use the 799? Which one? 799, good, because it is carbon dioxide. So we're going to use the 799 value. And last one, hydrogen, oxygen, single bond. Hydrogen, oxygen, single bond right there is 460. Plug all that into your calculator. And you should end up with negative 785 once you round to 3 sig figs. And these, of course, were all in kilojoules per mole. And there's your final answer. Count carefully. Draw your bonds. Count your bonds carefully. If you're worried about miscounting, do what I did and circle them. Make sure you don't leave one out or count one twice. Be careful with carbon-oxygen double bond, whether it is the normal carbon-oxygen double bond or it is the CO2 molecule, you're going to use a different number. Questions about bond enthalpy? All right, so that is it for Chapter 8.